Welcome back to RE7. If you've been following this channel, you know we've pivoted. We are no longer just looking at the surface. We are diving deep into the bridge between traditional mechanical engineering and modern Python automation. When I started in hydropower over 20 years ago, our tools were blueprints, slide rules, and eventually static Excel sheets. But today, the world of irrigation and large-scale M&E installations is changing. If you are a student in the US, the UK, or anywhere in Europe, you are entering a market that doesn't just want you to know how a hydraulic cylinder works, they want you to know how to simulate it before a single bolt is turned. Today, we are tackling one of the most powerful forces in nature, hydrostatic pressure. We are going to build a Python simulator to calculate the exact force required to lift a dam gate against thousands of tons of water. This isn't just a school project, this is a real-world safety protocol. Before we write a single line of code, we have to understand the physics. Imagine a vertical gate holding back a reservoir. The water isn't pushing on that gate equally. At the surface, the pressure is zero. But as you go deeper, the weight of the water above starts to stack. This creates what we call the pressure triangle. The pressure P is equal to the density of water, ρ times gravity, g times the depth, h. To find the total force pushing horizontally against our gate, we take the average pressure at the center of the submerged area. But here is the safety officer's secret that most textbooks leave out: the friction. When that massive horizontal force pushes the gate against its guide rails and rubber seals, it creates a stiction force. If you don't account for the friction coefficient of those seals, your hydraulic cylinders will stall, or worse, your pump motors will burn out trying to overcome a load you didn't see coming. As soon as our hydraulic cylinders start to lift that gate, the physics changes. We move from hydrostatics, water at rest, to hydrodynamics, water in motion. Using the Bernoulli equation, we can predict the velocity of the water rushing under the gate. This is critical for downstream safety. As an engineer, you have to ask, if I lift this gate 10 centimeters, how many cubic meters per second am I discharging? In our Python script, we aren't just calculating the lift, we are simulating the discharge. This allows us to prevent overtopping or downstream flooding. In the US, we use CFS, cubic feet per second. In Europe, we use cubic meter per second. Our code will handle both. Write your own prompt, or let AI handle it either way. AI can instantly generate the Python code you need for your calculations. It's faster, easier, and far more efficient than doing manual math. This Python program is a hydropower engineering calculator designed to estimate the lifting force needed to raise a dam gate and determine the required hydraulic cylinder bore size. It simulates the balance between hydrostatic water pressure, gate weight, friction forces, and hydraulic lifting capacity. Input parameters: what the user enters. The program asks the user for 7 inputs. Gate width, the horizontal width of the dam gate. Gate height, min. The total vertical height of the gate. Water depth at gate. How high the water is on the upstream side. This directly affects hydrostatic pressure. Gate mass kg. The weight of the gate itself. Seal friction coefficient dimensionless. Typical values. Rubber seals 0.2, 0.4. Steel, seal friction varies. This coefficient represents the friction between the gate and side seals. Hydraulic pressure, bar. The operating pressure of the hydraulic power unit. Converted internally to pascals. 1 bar equals 100,000 pascals. Now let's walk through the program together and run a full test using a set of standard input parameters taken from an actual real-world project. We'll enter these values into the simulator step by step, allow the program to process the calculations, and then review the results it generates. This will help us verify how the tool performs under realistic engineering conditions and demonstrate the accuracy and usefulness of the model. Engineering isn't just about moving water. It's about controlling it safely and efficiently. I hope this lesson showed you how powerful a simple Python script can be when backed by 20 years of field experience. If you found value in this Damgate simulation, hit the like button and subscribe. In the next video, we're going to look at HVAC load automation and how to replace messy Excel sheets with clean, scalable code.